Globally, we are going to face a number of big challenges in the next century, one of which is how to feed an ever-growing population. With a dwindling amount of available farmland and a changing climate, there is a need to look towards alternative growing, especially those which can be implemented off-grid in food deserts around the world. This is the long-term goal of innovative thinkers at the Biosphere 2. Here we have the Greenery S Freight Farm. This commercially available unit is a converted shipping container that now houses a state-of-the-art vertical farming system capable of producing up to 6 tons of produce annually, while only utilizing 5 gallons of water a day. The downside is a high energy consumption and reliance on grid power. This is where our project comes in. We have designed an agrivoltaics array for the Biosphere 2 location. This is the currently existing agrivoltaic system at the Biosphere 2, but what is agrivoltaics? Agrivoltaics is the combination of photovoltaics and agriculture, or solar panels and crops grown beneath them. The plants benefit from being in the shade as compared to the Tucson sun, while water use is decreased due to this as well. Additionally, panel efficiency is increased due to being cooled by the plants transpiring beneath them. For our particular design, crops that cannot be grown in the vertical farm can be grown under the array. These may include tall crops or those with more complex root structures, such as squash and potatoes. Agrivoltaics is a relatively new system that has yet to be optimized, therefore our design provides a new take that will contribute to the research front. Due to the space constraints at the site, the design will not be able to cover the freight farm's full electrical needs completely. It will instead serve as a proof of concept for the pairing of freight farms and agrivoltaics.
The design for the Biosphere 2 location consists of 61 solar panels and a second freight container to house all of the electrical components and serve as the sole transportation unit for the system. Within the secondary freight container are all of the electrical components, including a charge controller, DC to AC inverters, batteries, AC and DC disconnects, a thermostat, and an exhaust fan to cool the components. Taking into consideration component efficiencies and typical meteorological data, it is expected that the system will be able to supply roughly 45% of the freight farm's electrical needs. Assuming a conservative electrical consumption of 250 kilowatt hours per day. This number was determined using the industry standard PV watt tool for calculating solar energy production.
The electrical components of the photovoltaic system were all derated to a minimum of 25% of the allowable current. Additionally, the wiring for the system was selected to minimize voltage drop to below 2% as recommended by the NEC. We utilized NEC standard 690.12 to ensure our system has rapid shutdown capabilities, as well as 690.47 in relation to system grounding for photovoltaics.
The structure design was inspired by existing agrivoltaics designs, such as the one at Biosphere 2, which is pictured here. In our design, all these panels are supported by a team-developed structural assembly. Due to space limitations, we have 3 main designs: the 7-panel ground-mounted, 6-panel ground-mounted, and freight-mounted structures. A partial structural verification has been completed for each of these designs according to AAC 716 and IBC standards for the dead, wind, seismic, and snow loads. The partial verification involves pressure force applications, manufacturer load data tables, shear, moment, and deflection diagrams, as well as an overturning moment anchoring analysis. Additionally, hardware has been selected based on team member experience in working with these Unistroh materials. To further elaborate on the structural verification process, we worked extensively with the professional structural engineer from M3. A trade analysis was completed regarding the amount of columns included in the ground-mounted structure. As you can see, 3 columns on either side were able to support the structure safely while increasing the ease of access to the crop production area. Before implementing this full-scale design, a registered professional engineer would need to verify our calculations.
And this is where our structure would be going.
To demonstrate and test our full-scale design, we have created a functional model. This model represents the battery charging from both the power supply and the solar panels, which mimics our design. The model powers 3 components that represent the freight farm, which are the LED lights inside of the model freight farm, the water pump for the hydroponic system, and the oscillating fan. Our solar panels are supported by a scaled-down version of the unistrut structure that would go on top of the freight farm. It was constructed with unistrut beams, bolts, nuts, and spring nuts, mounting bases, solar clamps, and the adjustable braces. The board here shows all of the electrical components in our system. It includes a charge controller, an inverter, 2 watt meters, a DC power supply, a battery, an Arduino, and 3 plug-to-plug switches. The 2 watt meters collect data on the power output continuously. Our system runs to represent a full day of powering the freight farm, where the fan is running for 21 out of 24 hours, the LEDs are on for 17 out of 24 hours, and the pump is on for all 24 hours.
Overall, our team was able to 1. Determine design requirements for a fully off-grid paired agrivoltaics freight farm system, 2. Design a modular agrivoltaic system to provide power to the freight farm at the Biosphere 2 location, and 3. Scale the design for a functional model capable of verifying full-scale design integration. This full-scale paired agrivoltaics freight farm system design is a solid starting point for a build-out at the Biosphere 2 location. It will serve as a valuable research case study and could be modified for off-grid implementation in arid regions worldwide. Thank you so much for listening. We've enjoyed developing this design and hope you have enjoyed learning about our project as well as the importance of agrivoltaics in the future of our planet.